Okay, I will begin so that Professor Scherpen have full time to present this talk. So it's my pleasure to chair this semi-plenary session, which will be given by Professor Jacqueline Scherpen from Groningen University. So Professor Scherpen got her PhD degree in applied mathematics from the University of Twente, Netherlands, in 1996. And between 1996 and 2006, she had several positions in Delft Center, in Delft University of Technology. And since 2006, she is a professor at the Engineering and Technology Institute of the Faculty of Applied Mathematics and Natural Science of the University of Groningen, where she is director since 2013. She has many visiting positions in France, Japan, and United States, and her domain of interest is large, including model reduction for nonlinear system, realization theory, distributed optimal control with application to many domains like mechatronics and smart grids. She is also active in editorial board of many serious journals, prestigious journals like IEEE, IMA, Journal of Mathematics and Control. So her today's talk is about very stimulating topics about suboptimal, distributed optimal balancing between supply and demand in smart grid. So I'm sure that we are going to enjoy her talk. So please join me to welcome Professor Scherpen.
Now? Yes. Okay. Good. So, thank you for the introduction. To add, I'm also a member of the Jan C. Willems Center for Systems and Control in Groningen, which is actually a center which joins forces of several institutes within our faculty, where there's systems and control research done. I will talk about distributed supply-demand balancing and the physics of smart energy systems. The first topic is a bit more economic, optimal control, and the second topic is really based on physical modeling. And I will try to make some links there. This is joint work, which I did, among others, with Gun Larsen, Nicky van Voorreest, and, well, anyway, the whole list of people that you see here. I would like to also thank the organizers for inviting me here. This is one of my research lines. Actually, the distributed supply-demand balancing is a research line I started when I came to Groningen. And the topic of today is supply-demand matching at an economic level, distributed optimal control via ideal decomposition. That's what we're going to use, and we're going to a large effort that we do in this field is the modeling part. Then briefly, I will say something about the power systems approach via energy-based modeling. And this is useful for stability and for stabilization. And the question then is it also useful for optimization, pricing, etc.? So the coupling between these two layers is still somewhat unclear, but I will I will give some first directions to answers to this coupling in the end, and I will also pose some questions there. And then, of course, the question connected to that is, are these indeed two decoupled layers or not? If you talk to power systems people, they will say, this is a different layer. And if you talk to most of the implementation people, and if you talk to computer scientists, they are mainly interested in this part of the research. Okay, so first some introduction. I think by now most people know this. So we have a past and a future power grid. The past power grid is really, or sometimes we call it a dump grid. That's not maybe not the right word, but you have a central power plant via transformers and substations, and via high voltage transmission line, it goes to your home and to the buildings and office buildings, etc. And so that's the grid as we knew it, let's say 10, 15 years ago. It has changed. It's in a process of changing. So we're halfway here somewhere now. And you have all the solar panels, in particular in Germany. There are lots of solar panels on the roofs. There are windmills. There are still central power plants. Of course, there are industrial users which still use a lot of energy. But there are also the homes that like to produce their own energy and use it as well, have the benefits from that. There are electric cars introduced, etc. So there's the whole grid structure is changing, and we have to deal with it in one way or another. Right now, at least in the Netherlands, but in many other places, it's still not very smart. So there's a kind of over-dimensioning of the transmission lines and of the grid structure, so that it can deal with all these different types of energy supply that are nowadays available. But if you have even more energy supply, there are more people with solar panels, there are more people who produce their own power, but also there are more wind parks which have a more unpredictable behavior. Things have to change. Or you have to expand your infrastructure, and you have to improve your infrastructure, or you can say, okay, we're trying to do with the current infrastructure as much as possible, and we make our system smart so that we can handle with all these changes. Okay, so I'm going to talk about that, trying to make it a bit smarter, by looking at distributed optimal control of the power grid in the production side and on the demand side control. I will say something, because this is completely distributed, but of course there are many market models available right now, so I will say something about market embedding with a particular point of view that we take there. Then I will say something about grid integration, because we have been looking at the gas grid, distributed control of the gas grid, where you can think of embedding of biogases, etc., into the gas grid. And in addition, distributed control with power-to-gas facilities. And if you have power-to-gas facilities, you have a clear coupling of the gas and the electricity grid. And actually, for this part, we're already looking at so-called micro-combined heat power systems, which you can control. But these are systems that, at least in the Netherlands, run on gas. So there is already a coupling between the gas and the power grid. And then, as a final topic, I will say something about the physics of the power grid, which is a long-term research line that I have pursued, and where I would like to make some coupling between the ways, the points of views taken over here and over here. Okay. First, distributed optimal control of the power grid, the production side and the demand side control. I'm giving an example project, which we started already in 2009, which is the Flexiness project. And this project was motivated by the fact that actually gas is important in Groningen and in the Netherlands in general, because we have a very dense gas grid. This is not the same for all countries, but in the Netherlands at least the gas grid is quite dense. Almost every house is connected to the gas grid. So the heating and all the cooking, etc., we do on gas. And there's a business case here. There are a number of gas companies. The estimation was that in 2020, I should take away the hand. There's 1 million micro CHP units, which are micro combined heat power units in the Netherlands. These are units which produce heat and power in the same time. And in 2030, they expect 4 million of these devices. And when you have 4 million of these devices, you need to do something about that. Because 4 million also plugging their power production on the grid, on the power grid, that's quite a bit. And that can cause capacity problems. Okay, in that project we had there was a group of people developing energy management systems based on prices, helping the user to regulate costs. And in the same time, we have a network balance. That was our role. We have to look at the network balance and at prices of this thing. Okay. What are the issues there? So we have local production. We have lower transmission losses when you have local production. There's no longer centralized top-down control. End users will also be producers and also prosumers. Thus, that's what is called prosumers. So they are consumers and producers in the same time. We look at stability. We have to look at the stability of the network, and there's a clear need for coordination of these productions. Of course, here is what they call the market. Here are the controllable devices, and of course, here is the trading in between. Okay, and then in the time we started, there are actually a number of experiments in suburbs in Groningen, one of this is based on what is called the power matcher concept, which is households with controllable devices. All of these households had controllable devices and still have. The amount of field tests is kind of exploding right now. So you see them many places. You will see of these field tests popping up, and you will find all these households with controllable devices. It's a multi-agent. So the power matcher is a multi-agent accumulating bit curves in a tree structure, and the microeconomics is used to determine the equilibrium price. And so the prices are sent to some auctioneer, and then it goes back to the users. But what is the problem there is that there is no forecasting included and no prediction included in what's going to happen in the future. So we were interested in an alternative way of coordination, and we're thinking about distributed control. Local price communication between neighbors, for example, was a good option. And we had a micro-combined heat power system. This is one we have in our lab with a Stirling motor, which has an extended view. So we're not using it anymore. Which is a system which is an option for local production. So the overall efficiency can be as high as 90%, and the electrical output is typically 1 kilowatt hour. Okay, so what we want. If you want a stable network, first thing you want is the imbalance to be close to zero. So between the production and the consumption, there should be hardly any difference. In between the capacity limits, of course, of your grid. We want to avoid peaks, because peaks are in general not. You have to over-dimensionalize your transmission system to have peaks available in the system. So in order to avoid peaks, if we manage to avoid more peaks, we may allow more connections to one transformer, for example. If you have local production and local consumption, you have lower transmission losses. So there's local delivery. Of course, what we want is also delivery certainty. Nobody wants to be, so if the sun is not shining, that you're running out of power. Local optimization versus global optimization is a point we will discuss. So the problem formulation is as follows. I'm now formulating the optimal control problem. So if we minimize the imbalance, that was our original statement here, and the cost of production, then we have this optimization criterion. X is the imbalance, X transpose X is the quadratic form of that, and here you have the quadratic form of the production, cost of the production. Of course, you can add positive definite matrices in between here. So my X is the imbalance information. That's what we use here, because you can look at every household separately. And what is the imbalance in a household? Imbalance in a household at time k plus 1 is of course equal to the imbalance in a household at time k, plus the change in production, plus, and then of course we have a minus sign convention here, the change in demand. But then, if you do that separately for every household, you do not communicate with your neighbors about the imbalance. So what we say, okay, we weight our own imbalance, and we weight the imbalance of the neighbors. And so xi is what we call the imbalance information, and wi is the change in demand, which is actually, you can approximate as white noise, and ui is the change in production. And of course for the real imbalance then, the real imbalance we write with the tilde, aij is equal to 0 and aii is equal to 1. Now if you look at it from a graph perspective, this is the graph structure this is a possible graph structure you can have. So we have node 1, 2, 3, 4, 5. Node 1 communicates its imbalance with node 2, who's actually only communicating its own imbalance with itself. So there are self information, that's actually the AII, which is weighted on this edge. And what you see on these edges is the information of AIJ. And then of course you get an A matrix of this form where you have the zeros, and on the star places you have the AIJs. Okay, so, but we are talking about information of imbalance, and we actually want to minimize the overall imbalance. So why is that possible? Well, if we choose our weights, A, so I make my A a stochastic matrix. So my AIJ is not equal to 0 if and only if information is exchanged. All weights are non-negative. And all columns sum up equal to 1. And the graph corresponding to information matrix A is strongly connected. Because you need to be able to exchange your information with each other. Now if you do all this, then we actually have that the sum of all imbalances, the sum of all real imbalances is actually equal to the sum of all the information about the imbalances. So if your overall goal is to minimize the imbalance, you actually take care of that by the choice of the A matrix to be a stochastic matrix. So, okay. So this has game theoretic interpretation from economics literature, and you can also do dual decomposition on this. This is treated for optimization in the book of Boyd and van den Berge, although only for the static case. And based on price mechanisms in linear quadratic team theory and dynamic dual decomposition for distributed control, we then apply this to our setting. We also use distributed model predictive control with suboptimality and stability guarantees. And we recently applied this on the production side control with micro CHPs and heat pumps. And then we get the following structure. So if you look at the central model predictive control formulation, if you minimize from k to k plus n, and we sum over all the households, so these are the households, and we have a cost function here, such that for all I and t, so here we have the imbalance information equation, xi hat, and such that we fulfill all the constraints. And what type of constraints can you think of? Well, if you think of a micro combined heat power system, that is a system which has a bit of a startup time. And apart from that, when you turn it off, you have to leave it off for a while. So these are quite harsh constraints. Okay? Well, this is a central formulation. But if you have, as I said in the beginning, if you have 4 million households with a micro combined heat power system, this is not really feasible to solve. So then you can go to the distributed formulation, so that in the end every household can do their own optimization. And we minimize here over the controls, so that's the change in production of the micro CHPs. And here we have the sum of all the individual, we look at a local formulation. So we take the sum of all the individual optimization criteria, such that for all tau it holds that this equation is the case, where now the coupling with the neighbors is replaced by this VI hat. And, well, here we have the constraint equations. Okay, so this coupling is actually the crux for going to dual decomposition. So we use subgradient iterations to, because this VI, of course, this is an extra constraint. This VI should be equal to this sum. And that's what you see coming back here. So we have a Lagrangian multiplier, lambda I, and then this is in the end what you want to regulate to 0, because then you fulfill the constraint. If you solve this problem, you solve an optimization problem with this utility function. And then you can again see that if you manage to get the constraint, so to get VI equal to this, then this is equal to 0 and it's gone. And then the distributed optimization precisely solves your original global optimization problem. Okay, now if you look at the power grid, and the current power grid, you have the high voltage lines, which are then connected through transformers to medium voltage lines over here, and then connected to low voltage lines, also again via a transformer. And if you look at distributed topology, well, you actually have every node being equal. So there's no hierarchical structure in there. And so we first look at this possible topology, and then later on we look at how this could be embedded here. And of course, this type of topology is used a lot in by studying microgrids, etc. Okay. Now, what did we do? We have the heat demand to be leading for this micro CHPs. It's a constraint that is the heat demand has to be met with local devices. And the constraints on the production side, so that the micro CHP and the heat pump, so we also have heat pumps included, there's an off time and not on for a very small demand, for example. We have a maximum production level, etc. And some of these constraints are non-convex, so we're a bit in trouble. So we actually, when we solve this dual decomposition problem, we have here, then what we eventually solve is not precisely the same as the original central problem formulation, which was our original goal. But there is, so that is what is called the dual gap. We have information exchange with neighbors, whatever that may be. That may also be virtual neighbors, not necessarily physically nearby neighbors, though that would be good from a losses point of view. And via game theory and dual decomposition price mechanism, we have a price mechanism interpretation. The control of the imbalance can be done fully distributed at each household with only information of the neighbors. And the implementation is feasible, of course, while imposing constraints. So we managed to get some results there. So realistic electrical demand patterns we obtained from the Energy Research Center in the Netherlands, and what you see here is a typical demand pattern. No, sorry, pushed the wrong button. Is a typical demand pattern where you have people wake up in the morning, during the afternoon there's less, and then there's an evening. So this is a week. So there's the morning and the evenings have the largest peaks for demand, and in the middle there's less. Still, it has some kind of a stochastic flavor, and for using the methods, of course, we assume it's white noise, and of course you see it's not the case. But we assume that for the moment in order to be able to apply the methods. Now, if we apply now our optimal control, this is in the end what we see. This is the sum of a number of households. This example has this is one household in a network of, if I'm not mistaken, this one was with 20 households. So this is very small. A small microgrid, you could say. What happens then? The red one is the production. So you can see it's turned on and on. And it's, of course, it's negative. It's opposite to the blue one. The blue one is the demand. And the black one is the imbalance in the house. And you can see it always stays between these two. What does that mean? If you look at the zoom, you will always see that the black line always stays between the blue and the red line. So you're never able, of course not, because it's very stochastic, your demand, you're never able to make it completely zero. Nevertheless, you manage to reduce the burden on the overall central grid. And so you need less from your external power supplier. So the embedding of in the electrical power grid in the dual decomposition framework via distributed suboptimal control of the decentralized power generation can be achieved. The methods can also capture the current network structure, because if you look at the current network structure, the way to do that is that so we have actually a lot of freedom in this A matrix that we have. So in the graph connections. So we can actually say, whenever we go through a transformer from the low voltage to the medium voltage, we can say, okay, that's less advantages. So we weight the partners that go via the medium voltage, we weight them less. As long as you sum up to 1, you can play around with your weightings. You can actually, someone from here connected to Groningen, for example, you can actually give it a very low weight because you know it has to go a long way over the transmission grid, and that causes some losses that are undesirable, but you can still give it a very small weight if you want. So you can capture the current network infrastructure. The information from a physical faraway neighbors are then set to 0. This is promising with respect to computational complexity and reduces transportation cost, as I just mentioned. It proposes that the structure of the network in the future may change when there is a high share of controllable decentralized generation present. Well, I already said that in the beginning, that there have to be changes in the network structure. And if you do it completely in this distributed setting, then you really need to think carefully how to design a new infrastructure. So I'm not really thinking in these terms. I'm thinking more in terms of going through, trying to use the current infrastructure as much as possible. So this is published in IEEE Transactions on Smart Grids and in Applied Mathematical Modeling. So, what are the things to do? feasible and optimal storage topology to be incorporated in the modeling. And, well, there are countries that play around a bit with storage in with water, but that is something that you cannot do in the Netherlands because we are lacking mountains. So that's a bit difficult to be used. But of course it can be done with for example, transporting power through all the way to Norway, for example. But still, there are other storage topologies. So there's hard work nowadays on making new batteries. Of course, we have electric cars, which can be seen as storage. And they are getting in more and more. And in addition, and I will get to that later, we also have possibilities with power to gas. Okay, then there's to do with price interpretation. So actually these Lagrange multipliers are called shadow prices in the economic literature. But shadow prices are in fact so-called marginal costs. So I talked to some economists and they called it marginal costs made to decrease limitations and circumvent model bottlenecks. And then the question is, how do we translate this to a real price? Should we take the real price and then just take the variations of the real price with respect to the shadow prices, for example? Is that a possibility, or how do we do that? And then I'm thinking about every house has their own price. How to involve demand control? Well, that's not too difficult. Include additional models. And I'm going to show very briefly the demand side control with a washing machine. I'm just looking at demand side control now, not doing production side control yet, because the coupling in itself is possible, but requires a lot of computational efforts. If you look at the washing machines, here's again electrical demand for 250 households, different types of households. And we decide about the best starting time for a washing machine. So suppose 50% of the households do one wash per day. We explore the flexibility, and the household specifies just the end time of my washing. So we flatten. The idea is to flatten the net power load. So the household in the network is a subset of all households in the power network. There's two-way communication, and the global goal is to flatten the total power demand in the network. The local decision is when to turn on the washing machine. Demand is given by fixed demand and the flexible demand. The dynamics of the demand are given here, so these are actually the changes in demand, as you can see. And the change in the washing machine demand is given over here. So the F is the flexible one. The rest is given by the G. Demand information is given over here. Same story as before. So we're making this same information structure as before. When it's not loaded, it cannot run. When it's not running, electric demand equals 0. When it's starting, the run until end of cycle, etc. So this is something that needs to be considered. What is necessary here, and that's actually a problematic part of it, is the introduction of binary variables and if-and statements. So we have delta I is when it's 1, it's running. If it's 0, it's otherwise. And for example, there's number 3, which was starting, run until the end of the cycle. How we implement that? Well, in this way. And so my delta I is 1, and my T on is less than the overall program time. Then my K plus 1 is equal to 1. Of course, when this is finished, and the programming, the running time of the washing machine is over, this turns to 0. And this is for the implementation, actually, because we're dealing with mixed integer optimization, this can become problematic. So we have tried to do it as clever as possible with these deltas. In this way. So this is our implementation. Well, this is a typical pattern for a washing machine. So first it warms up. Then there is a peak after a while. And then there's a peak at the end, which is actually the centrifuge case. So it's the drying stage. So we have 50% load wash. Wash must finish before 4 hours and 40 minutes. The wash itself takes 1 hour and 30 minutes. And we take time steps of 7 minutes. And our simulation time was 7 hours. Okay. We're dealing now with we have chosen this particular A matrix structure, where we have weighted our own demand as 0.6 and the demand of the neighbors as 0.2. And of course we're dealing with the non-convexity case. Now if you look at the outcome, here the green line is the total demand, so that's the fixed demand plus the flexible demand from the washing machine. The blue dotted line is the non-shiftable demand, that's this one. And the red dotted line is demand from washing machines. When you don't do anything, you just plug in, put in your wash and you turn it on. And then also we did not model that they all turn it on loaded it in the same time. So we had some distribution there. Then you have this pattern for your washing machine. So all the washing machines are done after 300 minutes. But if you look here, the overall demand is the highest in this part. So it would be better to shift this towards the end. So with our method, we managed to shift it. And you see that most of the wash is done over here. There's just a little bit of washing done here. And you see here the shiftable demand. The overall demand is actually lower. And then you can see that also in your cost function. So this is the level of the cost function if you don't do anything, and this is the level of the cost function if you apply our methods. And the computations turn out to be well scalable. Okay, so a further study says actually that we must choose the information exchange matrix A wisely. So how can you do this in a way such that you have no problems with your computations? That's more or less the idea. And at the same time, you have as many connections as possible. We also need to include multiple types of devices. So there are nowadays refrigerators that you can regulate between 2 and 5 degrees. You have all air conditioners or heating devices that only heat between, for example, 19 and 21 degrees. And we connect, there are multiple types of devices that we can deal with. We also want to connect to local production of power, as presented before. That is ongoing work. The main problem there is that you have these harsh optimization problems, one with the binary variables, and the connection of them is not making the simulations easier. But we're working on it, and we're likely going to get some results soon. Scalability of the simulations. So far, simulations up to 10,000 households via parallel implementation goes well. So that's quite a large number. And we have a combination of the next step is actually how to combine this to hierarchical scheduling methods with distributed control, embedding in market structure. And what we say is the fit in what is called the Universal Smart Energy Framework. And then if you look at the embedding in a market structure, that's the next topic I'm going to actually briefly discuss. Because this is recent ongoing work. So the market in the Netherlands and in actually all countries in Europe is deregulated. although there are subtle differences between the different countries. Not always subtle, but anyway. There's a separate price for the network transport and energy delivery. Transport can be accounted for by choices in the A matrix. For example, low weight corresponds to expensive transport. However, the supplier market is deregulated. So physical neighbors may have different suppliers. How to embed distributed control algorithms in such a structure? And we have a collaboration going with in a project, in a consortium. One of the main partners is DNVGL, and they have set up what is called the Universal Smart Energy Framework. Whereas this is the so-called planning phase. This is the wholesale market is here. We have an optimization balanced responsible party. These are the balanced responsible parties are in fact the energy suppliers that you have chosen. And in addition, they have added aggregators, optimization aggregators. And here we have the prosumers. So that's the households, but it can also be factories, industry, etc. In addition, there's forecasts. Forecast, for example, for the weather. Forecast also for what type of demand there will be, if there, for example, is going to be a football match or not, and people are all watching the TV or not. So there's all this forecasting going on. There's a validation by a so-called distributed system operator. That is the one who takes into account that the capacity is the capacity of the network is okay. So the distributed system operator is in the region, looking at the region and looking at the capacity of the region. That is the validation phase. And then there's the operation phase, and that's merely what we are looking at. And in the operation phase, you have the imbalance market. And this is the TSO, the transmission system operator, who does imbalance detection, for example. Also, congestion detection is done by the DSOs, distributed system operators. So they really look at if there's congestion, do we have to maybe separate some region. These are the balanced responsible parties, so that's the suppliers of energy, that you are free to choose which one to choose. Here is a new layer with the aggregators. Right now, they're not implemented yet, but they are expected to be implemented later. And here we have the prosumers. And then you see here control signals, as they called it. There are, well, you could call it control signals, but what they came up with were so-called goal functions. And goal functions are the functions that relate to this forecasting. So they say, okay, if you are going to be very different from what you have promised, you will be somehow penalized. And that's why you get these goal functions from so in this hierarchical structure. Now we are looking at the operation phase, and we are thinking we have been implementing originally our optimization algorithms, distributed optimization, in here, in this layer with the prosumers. But now we also are going to include the aggregators and the balanced responsible parties. So there's an extra aggregator layer, distributed control per layer, combined distributed and hierarchical control, how to guarantee the performance. There's a goal function, initialized from day-ahead planning and then adapted in the operation phase, depending on the real loads. So it depends on both fixed and flexible load. And then the question is how to embed that. That's not a straightforward thing. And then the role of the DSO is to put capacity limitations. And of course you can put them in the constraints, but a feasibility analysis is needed for that. And also there's a complex part of it, you can put them in the constraints, but in which layer precisely, because as I said before, you may have a different balanced responsible party than your neighbor, but the DSO is responsible for both of you in the same time. So collaboration between market parties then is another part of this. Okay, so this is about the market structure. Now you can also think about how to do this with other types of grids. There's of course the gas and the heat grid. We've been looking at the gas grid. Smart gas grid project. We have local farmers producing biogas to optimize the real costs. High, medium and low pressure gas grid that we're dealing with. And what is the optimal size of storage in that case? And the inclusion of lorries picking up gas from farmers. So a microgrid for farmers and connection to the low pressure grid plus lorries to control capacity. You can see a picture here, not sure how clear it is, but you have prosumer 1 up to n, and the storage is here. And what is done? So the storage here is of course a dynamic equation. When you have biogas, of course it's produced, but then you are either bringing it to the storage or bringing it to your neighboring partners. You have to do the upgrading. You can bring it to the low pressure gas grid, and you can do some compressing and then bring it to lorries. Okay, so this we have looked at as well. And then finally distributed control with power to gas facilities, which is coupling the different grids. So power to gas offers opportunities for storage of power in the form of hydrogen and can be done locally. Hydrogen can be used for mobility industry, for example in hydrogen cars, injected into the natural gas grid, which is very limited, and reconverted into electrical power. That's another possibility. So you can inject only a tiny little bit of hydrogen in the natural gas grid. In the Netherlands it's 0.0%, 0.01%. I think in Germany it's a bit higher. I don't know how it is in Austria. So here we have the power infrastructure, here we have the gas infrastructure, here we have natural gas storage, and we have, you can get, through electrolyzers you can get H2, but you can also bring it back to power again, generate power from that. So schematically, it looks like this. I have the power grid here, bringing in solar, wind, other types of renewables. I have a surplus of power that can go into the electrolyzer. Hydrogen can be stored, but it can also be used for the mobility and industry. It can go into the gas grid, and it can be flared. Then you get rid of it. And from here, of course, you can also go again to the mobility industry and the gas grid, or you can go via a fuel cell and transform it back into power. This is a presentation that we're going to give tomorrow. It's actually a two-layer optimization problem, because we maximize the power to gas profit, but the DSOs of the different grids, so we have three grids, the power grid, the gas grid and the mobility industry grid, have to avoid overloading of the grids. And we use some results from this paper. What is also ongoing here is asynchrony in the information exchange. Okay, so this is part about the economic level, distributed optimal control via dual decomposition. Now briefly, I was planning to talk about the physics of the grid. A power systems approach via energy-based modeling. Starting research is useful for stability and stabilization, but is it also useful for optimization, pricing, etc.? So this is the question I posed in the beginning. Now, if you then look at the physics of the power grid, what is the typical way of modeling this? So this is a completely different approach, completely different point of view taken to these type of systems. There's a synchronous generator. That is the model of many of these power plants. And of course, you can also take into account models of inverters, etc., that you have, for example, for coupling solar panels to the grid, or including also wind power that goes via DC lines and then couple it to the AC grid. That's one of the issues that you have here. So from a power systems perspective, the models of the power systems, synchronous generators, are interconnected via transmission lines, often approximated by pi models. A resistor, an inductor, and two grounded capacitors. Okay, you can easily make a model of that. Classical models used by power systems engineers are not always suitable to study the embedding of renewables. Why? Because they have, in fact, what power systems engineers often do is taking lots of assumptions and taking away some of the transient behavior, some of the dynamics of our system. And by the embedding of the renewables, you sometimes excite those dynamics, and then you're in trouble. So renewables embedding are known to cause large fluctuations, sometimes causing large and not always predictable power outages. So how to understand the physics there? So it's, as I said, it's a complete jump from the previous topic. But control system study towards the oscillator and swing equations, that's done a lot, for example, by Dörfler and Bülow. And then the swing equations are actually quite limited because of the missing transient response of the electrical part of your system. So what we did is try to make a full model of these equations, so including the electrical part. And this is interconnected through the grid. However, stability analysis is only achieved for one synchronous machine connected to an infinite bus. And the way we try to do this is using the Port Hamiltonian framework, which is a framework which is based on energy, based on the energy in the system and the power ports in the system. And this energy is then useful to be used as a Lyapunov function, normally, if you talk about a single equilibrium point. What has also been done is frequency deviation coupled to pricing mechanisms and stability for the swing equations. So there's quite a bit of work on this already before, and I'm sure I forget lots of references because there are many more. So power systems in the grid, an example network. I have some loads and some generators connected through some buses. I can make a graph of it, and from this graph I can make an incidence matrix, and the incidence matrix together with the Kirchhoff laws give you an 8th order model of a synchronous generator, which is a Port Hamiltonian model of the overall system. Okay, nice. I would like to have used this Hamiltonian, which is the total energy then, as my Lyapunov function. However, we're talking about an AC system here, so that's a bit problematic because you have an angle which is constantly changing. The states of the synchronous generator are three-phase rotor and stator flux linkages, the momentum P and the angle theta. The state of the transmission lines are given by the flux of the inductors and the charge of the capacitors. And the inputs are the electrical field and a mechanical torque. Together with the incidence matrix, a full Port Hamiltonian model is obtained. I'm not going to give it here because it's really too much to explain. There are no equilibrium points. The angle, of course, constantly changes for a fixed frequency because we have a frequency of 50 Hertz. That's in principle the idea. That's what we want. And they manage to do that by this constant mechanical torque. There are angle differences between the generators. It's difficult still to handle that. And the stability analysis is not straightforward. Also not after a Park-Blondel transformation. So possible for synchronous machines connected to an infinite bus. under the assumptions that some losses are zero. And then we use forced Hamiltonian systems analysis. This is then the Lyapunov function, so it's the Hamiltonian minus some additional term, which is stemming from this forced case. So where the, yes, thank you, almost there. So these are the fluxes, the transformed fluxes, and as I said before, it's only valid for the synchronous machine infinite bus case. This is an ongoing investigation how to use the Hamiltonian in the multi-machine case. Under restrictive assumption, this is also studied in this paper, the multi-machine case. So the model is rather complex, but to consider utility optimization in the port Hamiltonian model can also be made, can be done with the swing equations. Only taking the mechanical structure into account, but the swing equation, so that's the problem of the swing equations, you only take the mechanical structure into account. You can couple it to inverters, for example, for the coupling of solar panels to the AC grid, and load models can be added, and that's quite recent work. But other optimization in relation to the frequency and in different settings are available. So there's a whole bunch of literature about this. The problem is, all static optimizers all are static optimizations. So the dynamics are not taken into account when you do the optimization yet. And this is actually a topic of ongoing work. And this is also, in my perspective, the way to couple this physics with what I've shown before with the economic layer. So you want to do the same type of, the same type of approach to do this. So here, the physics are then part of your dynamics in the constraint equations, whereas originally in the economic approach, the physics are hidden somewhat in the constraints of the system. So if you couple this in the right way, it's still not completely clear, but if you manage to formulate this also in an optimal control setting, then you can make some coupling. So how to proceed? Study the grid in a multiple generator case, multiple load case with different characteristics, the embedding of multi-terminal high voltage DC grid in the AC grid, how to couple the economic and physical layer, pricing via frequency deviations, for example, and how about voltage and angle stability? That's not a clear answer either. It does not have a clear answer either. And how to embed this in the market structures available. So many open questions, many topics to work on. So summarizing, supply-demand matching at an economic level, distributed optimal control via dual decomposition. I briefly went into the physics of the grid. I'm not sure if I managed to convey the message, but I do think that these two should be coupled in the long run, and they should be coupled in a more convincing way, because indeed optimal control, etc., should take the dynamics of the physics into account. And this ends my presentation. Thank you.
Okay, thank you, Professor Scherpen, for this nice, insightful presentation. We probably have time for one single question so that people can reach their next room. Any? Nobody? No question?
Yeah.
Okay.
What information do they share with each other?
Yes.
They share information about their own imbalance.
So, is there any privacy issues according to this? Like,
yes, of course, there is a privacy issue. So you have to be careful on how do you do the real implementation and privacy. Yeah, that should be taken care of. That's not taken care of by us yet.
and how do policy people look at that? Like when you talk to them?
I'm currently talking to people in social psychology and also some people in the legal department, and they are looking at ways of taking care of that. And also, the social psychology people look at what are the precise incentives to people and how. And I'm actually currently discussing with them what is the way to translate these incentives in such a way that you can actually put them in the in these algorithms. So there is some connection, but this is not my expertise. But I'm trying to work with them.